thin, if possible, narrow or thin, thin in the sense of T-H-I-N, thin. And when is absolutely mandatory to use this type of solution when I have cases with low H, low convection coefficient, and typically this is the case for when I have to apply natural convection with gases. If you remember, one of the first lesson, I show you a table in which I show you the convective coefficient for the different cases, and the worst case, that means for the lower H value, is for natural convection with gases. Here, as for efficiency, also for effectiveness, I can define an effectiveness star, so epsilon star, that means the effectiveness for the finite surface, including the base plus the thin area. Numerator is, as for the previous case, the actually transfer rate for the finite surface, so H, and then I have to multiply the delta T temperature, the temperature difference, by this bracket that include the area of the base that in fact is at temperature Tb, plus the area of the fin multiplied by the efficiency, because the fin is not at temperature Tb, but is at temperature difference that change along its length. At the denominator, I have to consider the area of the surface, of the finite surface, without fin. I call it A no fin. A no fin must be calculated as the sum of the area of the base plus the area of all the cross-section of all the fin. If I have 10 fins on this base, I have the area of the base plus 10 times the cross-section of one fin. Again, temperature difference and H coefficient. Simplifying the different terms, I obtain an expression which depends only on the area and on the efficiency of the fin. Last slide is how to select the proper length of the fin. Sorry. Okay, we know that along the length of the fin, the temperature decreases. For example, if I assume that the base of the fin has a temperature bigger than the temperature of a fluid, the temperature decreases along the length of the fin. Decrease, but I arrive at one length for which the delta T between the temperature of the fin and the temperature of the fluid is low. At a certain point, delta T is 0. That means that for this length, I have no heat transfer from the fin to the fluid, but also a portion in which I have a low heat transfer rate. So it's important to know this temperature profile because of, for example, this last part of the fin is absolutely no sense because it does not work. And also this one, it's important to verify if the, for example, there's also a question of, come si dice peso? Wait, I can find the words in English. Weight, sorry. Is a question of weight, for example. If the finite surface is a metallic finite surface, I have to think about the weight of the system. Adding things, I add materials, metallic material, and the weight is not negligible. So if I have a portion of fin that does not work so much, I have to think about the possibility to reduce the length, to reduce, for example, the size of my equipment, or also the weight of this equipment. It's okay? So the theory of the fins is finished. Any questions? No. Okay. So we start with the exercises. And I have to close here. And I have to open a paint file. Okay. The student at home see the paint file?
Sì, prof, si vede bene.
Ok, grazie. Fantastico.
Yes, sir.
Grazie mille. Okay, you have now the exercises file with the texts of the exercises on the Aula web. So if you want to download it, I show you now a moment. I have here the file and I show you. You find this file that is a file with all the text of exercises proposed in classroom, if I'm able to, because I have to change from one computer to the other. And so, for example, with different sections, with different topics. So now we are here, finite surfaces. Today we do this exercise and this one and this one, 3 exercises, I hope, okay? And I have vapor that flows inside a tube, a pipe, with external diameter, equal to 3 centimeters. So with internal diameter D1, external diameter, D1 equal to 3 centimeters. And the temperature of the base of this pipe, is TB equal to 120 Celsius degree. We apply to this pipe some aluminium circular fins. And the thermal conductivity of aluminium is 180 watt meter Kelvin. The external diameter of the finite surface is 6 centimeters. Wait. And the thickness, now I draw the sketch. The thickness is 2 millimeters, and the spacing is spacing is 3 millimeters. Sorry. Yes, 3 millimeters.
Hello, sir. We need the code for downloading the exercises from our lab.
So switch off the microphone, please. If you have question, you can ask to me. Otherwise, switch off. I can understand. You need an explanation or question? Good.
No, sir. We need the code for downloading the exercises from our lab.
No, the code. You know, is the same on the web where you find the slides. Is the same page in Aula Web where you find the slides, the file of the class notes. It's okay? Where you find the PDF files with the note, the lesson notes. Okay or not? Okay, if it's okay, close the microphone, please. Thank you. And with this spacing and this thickness, I obtain 200 fins for each tube, for each meter tube, per 1 meter tube. Okay, the external area, the external air has a temperature to infinity equal to 25 Celsius degree, and the convective coefficient H is equal to 60 watt over square meter Kelvin. Okay, how much does the heat transfer increase for 1 meter cube? I have to compare the heat transfer rate with no fin with the transfer rate with no fins with the transfer rate with fin. The two cases I have to compare. How much does the transfer increase for 1 meter cube? I do the sketch of the geometry that is not simple to do on this tablet, but I try. And sorry, here I have to do the thickness, the thickness of my fin. It's terrible, this drawing, but please try to understand that at the blackboard would be better. But now, using this electronic device, it's not so easy to paint, yes, to do good sketch. And this one, so D1 is the diameter of the pipe without fins. D2 is the diameter with the finite surface. Then I have T infinity H. Then I have T, that is the thickness of my fin, and the spacing, that is, sorry, no, the spacing is without the thickness. The spacing is just to this point. S is the spacing, and the base is at TB. Okay? Obviously, the shape is not in scale, this sketch. I have more fin because I have 200 fins for each meter of pipe. If you finish to copy, I can change my page.
Sorry, only one question. The temperature of the base represents the temperature of the tube?
Yes. It's the temperature of the tube at the beginning, before applying the surface, the finite surface, and will be also the temperature of the base, keep it at the same temperature, also with a finite surface.
Okay, thank you.
And now we analyze the case of no fin. So the first case is no fin configuration. It's very simple because I have to, for 1 meter cube, I have that the area, no fin, I call it no fin, and is pi d L equal to pi 0.03 by 1 because I consider 1 meter of pipe. And Q no fin is equal to H that multiply A no fin that multiply TB minus T infinite. And is 60 by 0.0942, 120 minus 25, equal to 537 watt. Now I want to calculate the second case, the second configuration, finite configuration. And I have to evaluate first the efficiency, and for this type of geometry I have to refer to the graphics that I showed you in the last theory lesson. You remember that I have this type of graph with efficiency. Here I have 100%. Wait, sorry. And efficiency has this behavior with a parameter. You find exactly this graph on the slides. Now I reproduce, not in a perfect way, absolutely, the graph that you have on the slides. And this graph gives us the efficiency of this type of fin that depends on geometrical parameters like this one.
Excuse me, ma'am.
Yes?
Okay. Can you please tell me this graph represent what versus what? I didn't get it.
What is this graph?
Yeah, what is it representing?
Okay, this one is I'm explaining to you. It's a graph which represents the efficiency of this type of finite surface. That means a circular fin applied to a pipe, a circular pipe, a cylindrical pipe, expressed as a function of different geometrical parameters. Okay, you can see here, for example, this is a geometrical parameter that takes into account some parameters. Oh, okay. Like, perché adesso non va più? Wait, okay, like the temperature, the T, that is the thickness of the fin, the R2, that is, according to the previous graph, to the previous sketch, is the radius of the finite surface, R1 is the radius of the pipe, and also as a function of, for example, the convective coefficient here, the convective coefficient, and also the material in terms of thermal conductivity. But if you have exactly this graph in the slides of the theory, and in the slide of the theory, you can read better that for this geometry, using this graph, the area of the fin can be calculated as 2 pi R2 to 2 minus R1 to 2 plus 2 pi R2 T. Also, this equation to calculate the area of a fin is on the graph. On the graph, you find details about how to calculate a fin and how to calculate L, that is 1/2 of the length of a fin, 1/2 of D2 minus D1. This is what you find in the graph. The graph is in the slides. Okay, now I have to do the calculation and I have to read this graph for my own values. You are ready? I can change.
Yes, please, Professor.
Thank you. Now, for me, L is equal to 1/2 of 0.06 minus 0.03 equal to 0.015 meters. The parameter that I have to read on the slide, on the graph, is this one, and I have to calculate it. And I obtain 2.07. Then I calculate the other parameter that I have to read on my graph, that is the horizontal axis, and is h, k by t, and for me is 0.015 plus 0.002 divided by 2, but multiply the square ratio of 60 divided by 180 by 0.002 and obtain 0.207. Introducing this value, this value and this value inside the graph, I can read directly from the graph that eta is equal to 0.96. Okay? Then I calculate for my case the area of the fin, that is equal to 2 pi 0.03 to 2 minus 0.015 to 2 plus 2 pi by 0.03 that multiplies 0.002, and I obtain 0.00462 square meter. Q fin is equal to eta, the efficiency, h, a fin, plus TB minus T infinite. This is for one fin, and is equal to 0.96 by 60 by 0.00462, 120 minus 25, equal to 25.3 watt for one fin. Now, I have to calculate now the area of the base. The area of the base will be pi d1 by s, one spacing, okay? This area of the base refers to one spacing because s is only, I show you again. This one is only this one, okay? The area of one space between two fins, because the spacing S is this one. Then I have to multiply by the number of spacing for 1 meter of fin. And the base is equal to pi 0.03, that multiplies 0.003. Equal to 0.000283 square meters. the heat transfer rate for the base associated to only, I repeat, this small portion of pipe, okay, not all the pipe, is equal to H, a base, TB minus T infinite, and is equal to 1.6 watt. When you finish to copy, I can change. Wait, I have to.
Just a moment, please. Just.
Excuse me, Professor.
Wait a moment, please. I arrive. Eccomi. Okay. What is? I can. I have not listened the question. Repeat the question, please.
Yes. In this page, we found two different values. Okay, 2 and 0.2. And after that, we went to the graph and found the efficiency. Am I right?
No, I can understand. Wait, because I have to increase the volume of my microphone, because otherwise I can. It's the maximum already. Okay, repeat.
In this page, we found two different values, 2 and 0.2. Am I right?
2 and 0.2.
Okay.
Where?
And after that, the blue line.
Okay. So yes.
After that, we used the graph and found the efficiency.
Yes.
But how do you know the efficiency is exactly 0.6?
No. Okay. It's okay. It's an approximation. From the graph, I imagine that more or less the value can be like this one.
Okay.
The graph that you have to use is the graph that you have on the slides, not the graph I draw here.
Okay.
Wait.
Thanks.
Wait. Allora, wait. I have to show you which is the graph. You see now the slide?
Yes.
Okay. This one. This one is the graph.
Okay.
Okay. I did a sketch now on the paint file, but you have to refer to this one. That is the optimum graph to be used. This type of graph can be found in the handbook and the different book related to heat transfer. Okay, you can find this type of graph for a different type of. Yes.
So for all kinds of things, we have different kinds of graphs, and we have to use them.
Yes, for the more common thinnest surface, obviously. But otherwise, if you buy a thinned pipe with this geometry, together with your technical sheet, you can find this type of graph. If you have a different shape, you find your own graph.
Okay.
Okay.
Thanks.
Nothing. You are welcome. Okay. Now you are again on paint. And for each pipe, we have 200 fins and 200 spacing for each meter pipe. So if I have to calculate the heat transfer rate that I call Q total fin for the finned configuration, I have to multiply 200 by 25.3 plus 1.6, that is 5,380 watt. So the total effect, that means the effectiveness, the effectiveness for this finite surface, that is the ratio of Q total, this one, total fin divided by Q no fin is equal to 5,380 divided by what I obtained with the first case, 337, equal nearly 10 times. So I'm able to increase nearly 10 times the transfer rate by adding this finite surface, by adding this system of fins on my pipe. It's clear for all of you?
Yes.
Now, new example. The new example, you can find the text also of this new example on the same file of it transfer exercises. And in this case, we have a vertical flat plate made in copper. Copper in Italian is rame, with K equal thermal conductivity 380 watt meter Kelvin, and 1 meter wide and 0.5 meter high. The temperature of the plate TB is equal to 90 Celsius degree. I have an extreme on this plate T infinite equal to 10 Celsius degree. I apply on the plate 34 rectangular fins according to the sketch I show you now. I have also in this case, please be patient with me because drawing on this on this tablet is not so simple. So the quality is not so good, but please. Wait. And this one is 1 meter. 1 meter. This one is 0.5. I have that. This one is 40. Again, not scaled, obviously. I have the thickness of each is 10 millimeters. And this length, the spacing, is 20 millimeters. TB is the temperature of a base. I have air at T infinite with H coefficient. And the material is copper. H is equal to 1,400 watt square meter Kelvin. And I have to evaluate the heat flux by doing an assumption. I do the assumption of adiabatic fin tip. So, which is the heat transfer rate if I assume adiabatic fin tip. This is how we have to, what we have to evaluate. You are ready to start with the solution? Can I change?
One sec, ma'am.
Yes. Okay. We know that, first of all, we have to evaluate some parameter for this geometry. Is the geometry is a regular shape with constant cross-section for which we can apply the analytical solution obtained during the theory lesson. So I have to evaluate the parameter of the perimeter that is equal to the height plus the wide, yes, high and wide, equal to 0.5 plus 0.01. Yes, sorry, I was thinking about it, 1.02 meters. Then the A, that is the cross-section area. Wait a moment, because I have to wait 1 moment. I go under the rain in Sunday with my children, and so now the effect is this one. But A, that is the cross-section of my fin, is equal to 0.5 by 0.01 and is equal to 0.005 square meters. Using these two values, I want to obtain M, that is the square ratio, or HP Ka. And I substitute numbers. The length is equal to 0.04 meters, and so ML is equal to 1.096. If you remember, the expression for the efficiency for this type of geometry with the assumption of adiabatic fin tip was the hyperbolic tangent of ML divided by ML. and I obtain 0.729 as efficiency value. Now we have simply to calculate the transfer rate as area base plus efficiency that multiply the area of fins by h TB minus T infinite. I have to estimate the area fins, this parameter here. And area fins is equal to n number of fins by the area of one fin. Yes. The area of one fin, another step, intermediate step. Okay. The area of one fin is equal to 2 by 0.5 by 0.04, sorry. Plus 2, but multiply 0.04, 0.01. And I obtain 0.0408 square meter. Adiabatic tip, this one excluding the tip of the fin that is adiabatic. So the area of the fins is equal to 34 by 0.0408. And this 1.3872 square meters. The area of the base now we have to evaluate is the area of the plate minus the number of fins that multiply A. A is the cross-section of one fin. And so we have that 1.1 that multiplies 0.5 minus 34 that multiplies 0.01 by 0.5. This one is the area of the base. That is equal to 0.33 square meters. Okay? When you finish to copy, A for me, this one is the area of the cross-section of one fin. Then I have the area of one fin, that means the lateral area of one fin. Then I have the area of all the fins, and then I have to evaluate also the area of the base. A lot of different types of area. This one is another color. Okay? Have you finished? Can I change?
Yes, I think.
Thank you. And finally, the last step, the Q is equal now to 0.33, the area of the base, plus 1.3872 by the efficiency, 0.729 by 1,400, and the temperature difference 90 minus 10. And I obtain 150.2 kilowatt. Now I want to compare, for example, the case of no fin, the case of a transfer rate for the no fin. And this is equal to the area, 0.5 by 1, the area, by 90 minus 10 by 1,400. And I obtain 56 kilowatt. So I increase 3 times with with fins, rate flux, rate transfer rate, increase 3 times. Me l'ho scritto? Non si capisce niente. 3 times. Ok. It's okay? Now, okay. Now, last example. I have to calculate, evaluate how much it's possible to increase its flux by applying on this geometry that I'm showing you a fin system. So I consider a cylindrical surface cylindrical surface that now I go on. And for each square centimeter of this surface, I apply a fin. So it's better to do the sketch of this system. I have a cylindrical geometry. For each square centimeter, I apply a fin. If I do a zoom of this system, I have this one is 1 centimeter by 1 centimeters. And for all this external surface of this cylindrical base, I apply one fin, one cylindrical fin, with diameter equal to 4.8 millimeters and length equal to 25 millimeters. I know that the material of the base has a thermal conductivity equal to 207 watt-meter Kelvin. I have an airstream, as usual, with T infinite equal to 21 Celsius degree and H equal to 140 watt square meter Kelvin. I have that the base, T base, is equal to 316 Celsius degree. So the situation is this one. I apply for each square centimeter of my surface, cylindrical surface, a fin with this shape described in the sketch. I know the thermal conductivity of the material, I know the temperature of the base, I know the T infinite and H. How much one increase the heat flux by applying this type of fins. Okay. Q, no fin. Okay, I solved the problem. I solved the problem considering one module of 1 centimeter. So I will do the calculation for 1 square centimeter of my cylindrical surface, okay? Because I'm interested in comparing the case no fin with the case with finned surface. So with this one, Q no fin is B H by A by TB minus T infinite, and will be 140 by 10 to minus 4. 10 to minus 4 is the area, 1 centimeter by 1 centimeter. Okay? That multiply 316 minus 21. And I obtain 4.3 watt. For 1 square centimeter. I don't repeat this point, but is the calculation for 1 centimeter. Then the transfer rate dissipated by one fin. I have to calculate the parameter as usual, P, that is, sorry, P, usually I use another manner too, okay, P, the perimeter, and is equal to pi by D, 0.15072 meter. The area of the cross-section of my fin is equal to pi d to 2 divided by 4, and is equal to 1.808 by 10 minus 5 square meters. As a consequence, I can estimate M, that is equal to HP divided by KA, 23.74 meter minus 1, and so ML is equal to 0.59. I can change. You finished to copy? This one is the 3. Yes, thank you. 3.1.
Ma'am, I had a question. How many fins do we have in this question?
How many?
How many fins are there?
It's not important because now we know that for each square centimeter we have one fin, and we compare the two cases with fin and no fin for 1 square centimeter. Okay?
Okay.
Now, we do the assumption of adiabatic fin tip again. Adiabatic fin tip. And the Q, the transfer rate for one fin, is equal to HPKA, isothermal tangent of ML, TP minus T infinite. This comes from the theory. And substituting numbers we found before. We find 15.8 watt. Now we want to estimate the Q total, okay? That is the area of the base plus the H, but sorry, no plus, multiplying. The area of the base multiplying H multiply T infinite, TB minus T infinite, TB minus T infinite, plus Q fin. And so is equal to 1 square centimeters minus 0.1808 multiplying 10 minus 4 and this one is the area of the base, but multiply was 140 TB minus 360 minus 21 plus 30.8, and I obtain 17.16 watt. If I compare this value, so the Q no fin was equal to 4.3 watt, the Q total with fin was equal to 17.18 watt. So this comparison refer for 1 square centimeters of surface. Okay, so I increase 4 times the transfer rate of my cylindrical surface. It's okay for all of you? It's clear for all of you?
Yes.
Yes.
Okay, now we start with another topic about theory. I can close here. Non mi ricordo più. No? No? Wait a moment. I open the other PDF file, the next chapter. That is the, wait. And okay. We start with the chapter of transient in conduction. Transient in conduction means that in this chapter the temperature field that I want to obtain depends only on time, depends also on time, not only on space. So we need to associate to the boundary condition also the initial condition to solve the problem. And the first example is a particular case that is called lumped system analysis. Lumped system analysis, that in Italian is corpo sottile. So someone of you Italian can remember this famous corpo sottile, that is the lumped system. And is a particular body and is an ideal body. That allow us to simplify the analysis in a lot of cases. Why is an ideal body? Because this body is considered as a lump. That means the temperature of all the points of the body are considered the same. The temperature is the same for all the points of the body. And the temperature as a consequence for my body, my lump body, is only a function of time. This obviously simplifies the analysis, but is not a real case. Why? Because to have heat transfer, in the reality, I need a temperature gradient in the body. So it's a sort of a simplification, is an idealization of a body. But later we study, we analyze when is allowed to use this simplification, this assumption. Now we start with the analysis. We imagine to have this solid body that is all at the same temperature, and at the beginning, the temperature of a body is, for all the points of a body, equal to Ti. This body is immersed in a fluid, and the fluid is at a temperature T infinite, and exchange heat by convection with this fluid by means of convective coefficient H. I have to write an energy balance for my lumped system, and I write that the heat transfer into the body, why? Because I assume it's the same if you do the opposite case with a body with a temperature bigger than the fluid. You have to change the sign minus plus in the two sides of the equation. But for me, now I assume that the temperature of the body is at the beginning lower than the temperature of the fluid. So the fluid heats the body. So the transfer goes from the fluid into the body. So this heat transfer for the time interval d tau, is equal to what? To the energy content variation of a body during the same time interval d tau. And now I have to write equations, and in particular I can write that the energy content variation in time can be written as a function of temperature, and in particular the density that multiply the volume of my body. The product density by volume gives us the mass, then C, that is the specific capacity of the material, and the gradient of the temperature in time. Temperature, I use the total derivative because temperature for us is a function only of time. The temperature of the body is only a function of time, not of space. The heat transfer rate, the first part, the first member of this equation, is equal to the Newton law. I can express it by means of the Newton law, minus, because if I use, as usual, T as the temperature of the body minus the temperature of a fluid, I obtain a negative value because the temperature of the fluid is bigger than the temperature of the body. I need minus to respect the physical sense of this process. Substituting the two expressions here inside the energy balance written at the beginning, I can obtain this equation. Okay, this equation is after having multiplying both sides by d tau, yes. Okay? It's clear for all of you up to this point? Now, I introduce an auxiliary variable, theta, as a function of tau. Theta, again, is defined as t minus t infinite. Why I use this additional variable? Because I observe that dt is equal to d of t minus t infinite, because t infinite is a constant, so it's the same. To have the same variable on the right side, on the left side, on the right side of the equation. In this case, by introducing theta, I can write the equation like this. I have d of t minus t infinity divided by t minus t infinity, and on the left side I take a rho, I divide by rho cv. Okay, nothing difficult. I call t minus t infinite, I call it theta, and it's a very easy equation to be solved, and is an equation which does not depend on space, so no boundary condition is needed. I need an initial condition to solve the problem. as initial condition, I know that for tau equal to 0, theta is equal to theta I, initial value, that was Ti, the temperature at the beginning of my body, uniform for all the points of the body, minus T infinite. By using this initial condition, I can integrate this equation from 0 to a generic instant tau, and I obtain the solution. This one is directly the solution of, of our problem. And taking the exponential of both sides and rearranging, okay, I take the exponential on this side and I obtain this one, and then I multiply by tau, by theta I, the right side, and I take the exponential of this side, I obtain this one that is nothing else below that allow us to obtain the temperature profile as a function of time of my body. So the temperature of my body starts at value Ti and then increase and tends to go to the value of a fluid, tends to the equilibrium with the fluid at temperature T infinite. And the velocity, the slope of this behavior depends on what? Depends on this tau zero. Tau zero is, tau zero, sorry, zero Italiano. Tau zero is this expression here. This is the exponent of this exponential formulation in the solution. That is called time constant. This time constant is the time at which the solution theta is reach the 36.8% of the theta I. Why? Because if I consider that time tau equal to theta 0, if tau is equal to tau 0, sorry, if tau is equal to tau 0, I obtain E2 minus 1. E2 minus 1 is exactly this number. 1 divided E is 0.368. You can verify. It's obtained, this number is obtained by putting tau equal to tau 0, that gives us E minus 1, and this is this number. Now, some physical, now this is a mathematical step, it's interesting, okay, it's important, because now we have a law to consider the temperature profile, but we are interested in the physical meaning, and okay, this is an explanation of the shape of a previous graph. The temperature of the body approach the ambient temperature exponentially. Okay, the velocity with which the temperature of the body change depends on tau 0. Large value of tau 0 indicate that the body temperature approach the ambient temperature in a larger time. It's interesting, this last part of this slide, the exponent. The exponent, I go back here, and is exactly this one. The exponent can be split in different parts. I can rearrange this exponent introducing two numbers, two groups. And can you recognize the two groups? Someone recognize which is, for example, this one, this number, and this number? Okay, it's me that say to you that introducing the characteristic length of a phenomenon, that for a lumped system is the ratio between the volume and the external area. If I introduce this characteristic length, this one is the Fourier number. The Fourier number, that is a manner to non-dimensionalized time, is the dimensionless number that to introduce time in the analysis. This other number is the Bayeux number. This is important in this type of, in the lump system analysis, is the Bayeux number that is important. And here I explain to you why we have to use this Bayeux number. Because at the beginning I say to you that this type of analysis is an ideal analysis. Nobody can be considered as a lumped system actually, really. But for somebody, for some bodies, this can be a good approximation, which is the criterion to select when I can apply this approximation or not, is the Bayeux number. Look at this sketch. This sketch represents two thermal resistances. The first one, this red one, is the conductive thermal resistance that link the temperature of a body, internal temperature of a body, to the surface temperature of a body. Okay, and is the conductive thermal resistance, which depends on which? On the shape, the dimension of a body, and the thermal conductivity. So this thermal resistance can be written as LC, defined as previously as the ratio between the volume and the area. More compact is the body, better is the approximation of lumped system, divided by the material property, the thermophysical, the thermal conductivity. Then I have another thermal resistance, convective one, that link the surface temperature to the temperature of a fluid. This thermal conductivity, this thermal resistance can be written as 1 divided H the convective coefficient, okay? And if I put in the numerator this expression and the denominator the expression of a convective thermal resistance, I obtain exactly the Bayeux number. So the Bayeux number can be seen as the ratio between the conductive thermal resistance and the convective thermal resistance. It's okay for all of you up to this point? Why I'm interested in the comparison of the two thermal resistances? Because if the conductive thermal resistance, so the red one, this one inside the body, is low, that means that the temperature inside is nearly equal to the temperature on the surface. That means that the body can be considered as isothermal. The difference between the different points of the body is not so high, and the temperature can be considered as isothermal, and the body can be considered as a lumped system. So, but how low must be this value of Bayeux number? The criterion is Bayeux number less than 0.1. If the Bayeux number is less than 0.1, means that the internal conductive resistance is sufficiently lower than the convective external one. That means that the temperature field inside the body is nearly uniform, is nearly at the same temperature. That means that I can apply the solution obtained for the lumped system. It's okay? And which are the parameters which define the Bayeux number? The shape in terms of LC, volume divided by external area, the convective coefficient outside, and the material of the body, obviously. This number is similar to another dimensionless number. You remember something about it? You have the Nusselt number, is absolutely similar to this one, but the Nusselt number has H and K of a fluid. The Bayeux number has H of a fluid, K of a solid body. Okay, the difference between Bayeux number and Nusselt number is that the Bayeux number considers H of a fluid, obviously, and K of a solid body. Va bene. Wait, yes, last slide for today. I have introduced for you another dimensionless number that was the Fourier number. Here, you remember that the exponent of the law for the lumped system can be written as the product between the Biot number, now you know what is a Biot number, and another number that was, I say to you, that is the Fourier number. The Fourier number is this one. Is written as here. Alpha is the thermal conductivity by the time divided by the characteristic length to 2. This one is a bit complicated. After multiplying, dividing some for the same numerator and denominator, I can obtain at the numerator the rate at which heat is conducted across the body, and at the denominator the rate of which the heat is stored. So this one is only to say to you, the Fourier number gives us an idea to the behavior of a body in terms of heat conducted divided by the heat stored. Larger the Fourier number, faster the propagation of heat through the body. Finally, we will use the Fourier number. The Fourier number sense will be clear for you later during the different cases in introducing the dimensionless analysis. But at this moment, only is to remember that finally the lumped system analysis can be written, the solution of the lumped system analysis can be written in this way by substituting the exponent Biot number by the Fourier number. Okay, we stop because now we have to start with the semi-infinite solid, and I think that we can stop for today. See you next Monday. I hope that more than one student in classroom, and have a nice week. See you on Monday. Bye-bye to everybody.
Thank you, Professor. Have a nice
Grazie,
weekend.
professor.
Thank you.
Grazie.
Thank you so much.
Ciao.
Thank you, sir.